The James Webb Space Telescope has made history by discovering the earliest black hole known in the universe. This infrared observatory found a massive black hole that existed when the universe was only 470 million years old, roughly 3% of its current age. The discovery became even more intriguing when scientists measured the black hole's mass, which turned out to be 40 million times that of our Sun. This is 10 times the mass of Sagittarius A*, the supermassive black hole located at the center of our galaxy. This finding appears to have resolved one of the most significant mysteries in astronomy, the origin of the first black holes in the universe. But how did such a massive black hole form so quickly in the baby universe? What's so puzzling about the mass of this supermassive black hole lying at the edge of time? Finally, and most importantly, how does this discovery shed light on the birth of the first black holes in the cosmos? The origin of supermassive black holes has been a challenging question for astronomers. Two models have been proposed to explain their origin. The first possibility is that these black holes result from the collapse of the first stars, known as light seeds. However, there's a timeline issue with this theory. According to evolutionary models, the first stars formed approximately 150 million years after the Big Bang. These early stars were likely quite massive due to the conditions of the early universe. Allowing around 50 million years for these stars to evolve and reach the final stages of their life cycles, light seeds would form roughly 200 million years after the Big Bang. However, it would likely take several billion years for these light seeds to accumulate enough matter from their surroundings and grow into supermassive black holes. So the discovery of supermassive black holes by the James Webb Space Telescope in the first 500 to 700 million years post-Big Bang questions the validity of the light seed model. Could it be possible that the first black holes rapidly accumulated a vast amount of matter, quickly transforming into gigantic black holes? The answer is no, due to a limit known as the Eddington limit. Accretion occurs when the intense gravity of a compact object draws material from a star towards its core. Due to the conservation of angular momentum, this material doesn't fall directly into the core but instead forms an accretion disk around the object. As the disk accumulates material, gravitational potential energy is converted into heat, leading to the emission of thermal radiation, often as X-rays in the case of black holes. The Eddington limit, however, governs the luminosity of accreting black holes. This limit arises from the outward pressure of radiation, which balances against gravitational pull. So, when the radiation pressure surpasses gravitational attraction, accretion halts, as does the associated brightness. Consequently, exceeding the Eddington limit is typically considered implausible. This leads us to the second possibility for the origin of supermassive black holes, the direct collapse of massive gas clouds into black holes, known as heavy seeds. These gas clouds are initially quite huge, allowing them to potentially evolve into enormous black holes within the required timeframe. However, the challenge was the lack of concrete evidence supporting this theory of black hole formation. This is where Webb's data comes into the picture. To solve the mystery of the earliest black holes, the James Webb Space Telescope joined hands with the Chandra X-ray Telescope, designed to detect X-ray emissions from high-temperature regions of the universe, such as the accretion disks of black holes. The most exciting part of this discovery is understanding how we were able to see the black hole. For that, scientists utilized the magnifying power of cluster Abell 2744, located around 3.5 billion years from us. This phenomenon, known as gravitational lensing, occurs when the immense gravity of massive foreground objects bends or deflects the light from objects in the background. While this can distort the images of these background sources, it also magnifies them, making it possible to observe distant objects in greater detail. Telescopes like Hubble and Webb use this natural magnification to study objects that would otherwise remain hidden. Returning to the discovery, a massive galaxy cluster acted as a gravitational lens, magnifying the galaxy containing the massive black hole by a factor of 4. Follow Arrowway for Part 2.